Hi everyone. Today we'll be taking a look at geometrical probability and complements. So there are two subparts. We'll take a look at each one of them one by one. So starting off is probably the most simple thing. I'm sure you've learned it before, called the complement of an event, right? So the complement of an event A with respect to a sample space S is a set of all elements of S which are not in A. Now this is really wordy, but in a simple words, its complement is whatever is not in a particular element event, right? It's whatever is not there, right? The remaining parts. So you can see the denotions how it is oftentimes written as. So the most common part you will common denotion you'll see is probably the A with the apostrophe. So that's the most common one, and I'm sure you remember that A probability of the complement of A is just the same as 1 minus probability of A, or oftentimes it's written as probability of A and its complement A dash is equal to 1, right? Another way of looking at it is, let's say you have a sample space which has numbers 1, 2, 3, 4, 5, 6, and A accounts for, let's say, 1, 4, and 5. So A dash will have everything but A. Everything but A. So it'll just be S minus A, which means it's gonna have 2, 3, and 6. I hope that makes sense, right? It's super simple, nothing too complicated. I'm sure you've uh, seen this before. That's why I'm just keeping it really short and simple. Okay, so let's take a quick example question, just to jog our memory as well. So there are four letters and four addressed envelopes. The chance that all letters are not dispatched in the right envelope is what? Okay, so we have four letters: letter 1, letter 2, letter 3, letter 4. And we have four respective envelopes which it's supposed to go in. Let's say one to your father, one to your mother, one to your sister, and one to your brother, right? 2, 3, and 4, right? So let's just create a hypothetical situation for us, okay? Let's say letter 1 is supposed to go in an envelope 2, okay? Okay, let me change the color. So let's say letter 1 is supposed to go in envelope 2. Let's say envelope 2 is supposed to go in envelope 4. Let's say letter 3 is supposed to go in envelope 3, and letter 4 is supposed to go in envelope 1. So this is the correct order. Okay, we know this is how it's supposed to be. But let's just assume that we were randomly putting them in, right? So we know that for a fact that there is only one correct arrangement, right? There's only one correct permutation of how the letters can go into the envelope. There's only one correct way. Let's say first one is correct, second one is correct, but these two are swapped. Well, then it's gonna be a wrong. Then the entire thing is gonna be wrong, right? We can't have two letters going to the right people and then two letters not. Every single letter needs to go to the correct designated person or in the right envelope in this situation. So what we can understand is that there is only one correct order, right? Or arrangement. One correct arrangement. This is what we know, right? And how many total arrangements are there? Well, there are four empty slots, right? So think of it, it's like the same way as how we did our permutation combination. Remember, a lot of probabilities going to be using permutation combination. They go hand in hand. So if you are a little cloudy on permutation combinations, little low in confidence, I highly suggest you check that playlist out. I've showed how to solve these questions, right? Once you take a look at those questions, it's a lot easier to solve probability questions as well. Okay, so there are four empty slots for each envelope, right? Two, three, four. Well, how many different ways can there be arranged? Well, four, three, two, and one, or essentially four factorial ways, right? Which is 24. So there's one correct arrangement, 24 possible arrangements. Well, then, the way of dispatching them in the right envelopes is 1 by 24. But we're asked for not dispatched. So what we're looking for is kind of like the complement. 1 minus the correct probability, right? Probability. Assuming, obviously, this is all in the assumption that you're just randomly allocating one letter to one envelope, without even looking. This is all under the assumption. Obviously, if you know that letter one is supposed to go in envelope two, you can't mess it up. But let's just assume, that we're working in a random situation where we're not controlling anything. Everything is happening in a fair, uh, you know, probabilistic manner. Okay, so this is what our answer is supposed to be. So now what do we have? Well, we have 1 minus 1 by 24, giving us, a final answer as 23 by 24. So the probability that the letters are not dispatched in the right envelope is 23 by 24. Again, this is all under the assumption that everything happens in a random fashion, right? Okay, so a quick detour that I wanted to add in this video tutorial was odds in favor and odds in against. Again, this is nothing too crazy. It's just a simple thing. Well, what are odds? What does it mean when you say odds are in favor of it? Well, you say the chance, the chance of favorable outcome, favorable outcome by chance of unfavorable, right? It's not total now, it's unfavorable. Okay? Again, nothing, there's no rocket science behind it. It's just a terminology that you should be aware in case if something comes up. It's just something, like that. Because then once you know what it is, then it's really easy to, work your way on it. You really don't need to memorize anything at this point. So again, unfavorable in this case, odds against unfavorable by favorable. That's all it is. That's all it is. Okay. Okay. So now let's look at this question. A pair of fair dice is rolled. Find the odds against getting a total greater than or equal to 9. Now, I just explained what odds in favor and what odds in against are. I want you to pause this video and give this question a try. Odds against mean? Well, it means unfavorable by favorable, right? It's just a ratio, okay? And yes, it can be greater than 1. It's just a ratio. It's not a fraction or anything. You can just treat it as a normal ratio. So, if you remember, there's a shortcut that I showed in the last video. If you don't, it's okay. Well, for the pair of dice, being rolled, because it's such a common thing, you can just have this memorized. If you roll 2, 3, 4, 5, 6, and then I think 12, 11, 10, 9, 8, and 7 is here. Okay, so the chance of occurring is 1. Here it's 2. Here it's 3. Here it's 4. Here it's 5. Here it's 6. So here it's actually 1 and 1 each. So 2 plus 4 plus 6 plus 8 plus 10 plus 16. Kind of like that. Okay. Now, we need find the odds of getting a total greater than or equal to 9. So let me change the color. So we need, let me make it green. Okay. So we need 12, 11, 10, and 9. Okay. So what is the total that we get? Well, we get favorable is 10. How much unfavorable? Well, we know that there are total 36 different possibilities, right? Out of them, 10 are favorable, so the remaining are going to be 36 minus 10, which is 26. And now, using the formula, odds against, it's going to be 26 by 10. If you want to, make it into a ratio, you can have it 13 by 5. That's the odds against. Okay, super simple, nothing too crazy. I'm sure once you know the terminologies, you can solve these questions without thinking too much. Okay, now on to the main part is geometrical probability. Now, geometrical probability does or can sound a little daunting, but It's really simple, okay? Let me break it apart in the three dimensions that we usually work in geometry with. Well, we have our one dimension, right? Which is a straight line, right? We have our two dimensions, squares, rectangles, circles, and our three dimension, spheres, cubes, pyramids, all sorts of those things. So in one, if I'm going to talk in terms of one dimension, it's just, favorable length over total length. Okay? And when I say this without any context, it sounds really confusing. Okay? So just bear with me for like the next few minutes. Once we start doing the questions, you don't even need to come across, or this part that I'm explaining is going to be seem so redundant that you won't even need to listen again. Okay? But just stick around. You'll be able to connect the dots. Okay? So we have favorable length or total length. Similarly, in two-dimensional, we're gonna have favorable area, area by total area. And you guessed it right, favorable volume by total volume. Okay? It's the same idea, just goes from one dimension to two dimensions to three dimensions. Okay, let's start with the question. Super simple. I after solving this question, you can probably extrapolate the methodology to one dimension and probably three dimension as well. Okay, so what we're given is a square is inscribed in a circle. Okay, if a point is selected inside the circle, then what is the probability that the point also lies inside the square? Okay, let's break it down. Okay, so what are we told in the first sentence? That a square is inscribed inside a circle. Well, what does inscribed mean? Well, it's going to look something like this. I'm going to have a square. Okay, I'm going to try my best. Square. And I'm going to have my circle like this. Okay, this is the center of the square and the circle, right? It's not the best drawing, please forgive me, but this is the idea, right? This is what we're told. Now, if the point is selected inside the circle, then what is the probability that the point also lies inside the square? Okay, so we're told that a point is selected anywhere in the circle, okay? And now we have to find that it should also, what would be the probability of it being in the square as well? Well, remember what I showed in the last slide. It was just favorable area by total area. Okay, let's break it down. Let's take, we really don't need any numbers. We can work with variables in this case. Okay, so what I'm going to do is I'm going to erase this shaded region that I've drawn right here. Okay, and after erasing it, I'll change the color as well. So let's for now assume that this is my radius r. Okay, so my total area, well, that's gonna be really simple, right? It's gonna be pi r squared, right? Because my square is inside the circle. So when so anything that's inside the square is going to be inside the circle. But that doesn't mean everything inside the circle will be inside the square, because they still have this area, which is not part of the square, but it is part of the circle. Okay, so that's why I'm going to take the bigger area, which is it's the circle. If the circle was inscribed in the square, if it was maybe something like this, then I would take the total area to be this area of the square. I hope that makes sense. Okay, now how do we find the favorable area? Well, we just need to find the area of the square. Let me change the color. Let's make it a little colorful. Okay, I need to find this area, right? This area. Well, I know for a fact that this is r. Okay, I know this is r, so that's kind of like the hypotenuse. So let me make a bigger square here. Okay, let me make a bigger square. So this is gonna be 2r. And I know this is a square, so this is gonna be 2r by root 2. And this is gonna be 2r by by root 2. How do I know that? Well, I'm just using trigonometry. I know this is 90 degrees. This is 45, 45. If you know your 45, 45 relation, you know that there's a ratio of, the relation is between by multiplying a root 2 or dividing a root 2. Okay, so I know this length is now 2r by root 2, or it's the same thing as r by root 2. Okay, this is what it is. So this is one side. Similarly, the other side is also r root 2. Okay, so my favorable area is going to be r root 2 whole squared. Now let's bring it down here. So I'm going to have probability is going to be r squared in times 2, because square root of 2 whole squared is 2 by pi r squared. Cancel, cancel, and I'm left with 2 by pi. So the probability that the point also lies inside the square is 2 by pi. It's kind of like, like 2 by 3.14 if you want a better approximation, but I'll stop it here just because it really doesn't make sense using a calculator at this point, because I'm trying to explain the whole concept here. Okay, again, it was a really simple question. It may have seemed really confusing at the beginning, but now that I've broken it down of what I'm doing, I hope it makes sense. Now a trick question in this situation could be saying that, square is inscribed in inside a circle, and if a point is selected in the square, what is the probability that it also lies in the circle? I'm just replacing, the square and the circle here with each other. Okay, in that case, the probability would be 100%. Why? Because if it's inside the square, it by default is going to be inside the circle, right? It's the square is already inscribed inside the circle. Again, it's really unnecessary, but I hope, like, I'm trying to get the point home right at this point, at this level. Okay. Okay. Next question. So a point is chosen inside the circle. What is the probability that it is closer to the circumference as compared to the center? Again, if you're confident after solving the previous question, I highly recommend you pause the video, give it a shot. Okay? So let's say we have a circle. Okay, I'm going to draw it a little bigger this time. Okay? This is the center. Okay? It's saying, what is the probability it is closer to the circumference as compared to the center? Okay, so if it's closer to the circumference, I'm going to have to divide, and this is my radius, for example. So if this is my radius r, okay, right? This is my radius r. I'm going to have to break it in by half, right? So now, if I'm going to draw a dotted line like this is going to be r by 2, okay? So any point, here, let me change the color. Any point in this green area, it's enough. It'll suffice the condition that the question's asking, right? Because any point in this area beyond the dotted line and inside the circumference is going to be closer to the circumference rather than the center. Okay, so this is my situation. I've already got it. Now I just need to make it convert it into math. Okay, so favorable area, right? Favorable area by total area. Well, what's the total area? Again, it's gonna be pi r squared, right? And I need this green area. That's my favorable area. So my green area is going to be, I'm going to take pi r squared, right? And I'm going to subtract it by pi r by 2 whole squared. I hope that makes sense. Because what I've done is I've taken an entire circle and removed this smaller chunk that I've circled. I'm shading in blue right now. Okay? That's what I've removed. So what am I left with? I'm going to remove the pi from all of them. I'm going to have r squared minus r squared by 4 by r squared. Okay, so 3r squared by 4 by r squared. Okay, and the probability is going to be 3/4 or 75%. Okay, so again, a super simple question. It seemed really confusing at the beginning. It may have seemed really confusing at the beginning, But once you break it apart, once you understand what they're really asking, it's not that really difficult. I mean, once we figured out that, this is the favorable area in the one and green and the total area, we just had to get the relations in the correct fashion and simplify it. Okay, let's do something a little different now. Okay, so we're told that if p as a constant is chosen at random in between 0 and 5, what is the probability of the equation to have imaginary roots? So again, I highly recommend that you pause the video and give it a shot. Okay, so let's break it down. First of all, we're told that if this we need this quadratic to have imaginary roots. Well, what is the first requirement for imaginary roots? Well, that the discriminant should be less than 0. What's the discriminant? B squared minus 4ac. Again, this is all from my quadratics video in the functions playlist. You can have a look at it. Okay, so b squared minus 4ac should be less than 0. That's about it. Okay, so we're told. So now what is my b? My b is p. P squared minus 4 times 1 times c. C is p plus 2 by 4. Okay, should be less than 0. Okay, so 4 and 4 cancel out. I'm left with p squared minus p minus 2 should be less than 0. Okay, let's solve this in a quadratic. So what do I have? I have p minus 2 and I have p plus 1, I think. Let me just check it out. P squared, and then I have minus 2p minus 2, and then I have a plus p as well, so minus 2p. Okay, this looks good. So my critical points will be p is equal to 2 and p is equal to negative 1. Okay. All right, and it's going to be less than, so it's going to be between them. Okay, so let me draw my number line. Let's draw a number line. I'm going to draw it in white. Okay, so I've told that p can be between 0 and 5. Okay, so let's take this to be negative 1, 0, 1, 2, 3, 4, 5. Okay, so my allocated area which I can work under is this, or the length that I can work under is this. Now my solution is coming between minus 1 and 2. So it's this part. Now, what is, again, it's the same thing. Now you might be thinking, how do I, find favorable area or whatever? No, there's no favorable area. Now it's one dimension. So it is favorable length by total length. What's my total length here? It's from 0 to 5. It's this one in the bracket in the white. So I'm going to have 5 units. And how many of those 5 units are actually being satisfied by the condition that I've done in red? Well, that's just 2. It's 0 to 2, right? This part. So my probability is 2 by 5. It's as simple as that. That's it, 40%. That's the probability that this equation will have imaginary roots. Okay? I hope that's clear now. Let's go to the next question. Okay, so we're on to our final question for today's video, and we're asked that a cone of maximum volume is inscribed inside a sphere of radius r. If a point is chosen inside a sphere, then what is the probability that it also lies inside the cone? So if you think about it, if you just pause the video and think about it, it's very similar to the question we had previously with the square and the circle. The only difference now is now we're working in 3 dimension, and we're told that a cone of maximum volume. That means we have to maximize the cone as per the situation. Okay. So again, how can we start? Well, the probability is basically volume of the cone that's maximized, right? Maximized by the total volume. What's the total volume? That's the volume of the sphere. Well, what's the volume of the sphere? That's really simple. It's going to be 4 by 3 pi r cubed. Notice I'm using a capital R, okay? Because I'm going to use a small r again for the cone, but that's going to be a variable r, okay? I'll just mention it here. Capital R is constant, okay? That's not going to change because that's the radius of the sphere, okay? We're working with the assumption that the sphere has a fixed radius and a fixed volume, and we're going to maximize the cone inside it with the variable r, okay? With the variable r. Okay, so what's going to be the volume of the cone? Well, that's going to be 1 by 3 pi r square h. Okay, that's what it's gonna be. Now I have this variable and this variable. Okay, now I can't really, maximize it right now. It's a little confusing. How can I do this? How can I do this in a really simple fashion? Think about it right now. If you need to draw it out, let's draw it out as well. Okay, so let me change the color. Let's take white to draw the sphere here. Okay, so we have a sphere, this. Okay, and let's draw a cone, the base of the cone. Let's just take it, for example, let's maximize so it's touching it. Okay, so this is the center of the sphere. So this part is, let me change the color, let me make it yellow. This in yellow here, this line with the dot is our capital R. Okay, this is our capital R, and this is our small r. That's the radius of the cone. Okay, capital R is the radius of the sphere. Okay, this entire is my height. Okay, I hope that makes sense. Okay, so, and this is my radius again. So from here to here. Okay, I know it's really hairy, so I recommend that you draw it out as you're also solving it, so it's much more easier to work with. Okay, so this part can be called x if I want to. Okay, so what I can say is x plus h, or x plus r is equal to h. X plus r is equal to my height. So my height is equal to, right, x plus r, right? That's what it is. So this part maybe could go here. Okay, now what would be my relation with x, small r, and capital R? Well, I can use the Pythagorean theorem, right? I get x squared plus small r squared is equal to big R squared. Big R squared, like this. So what I have is r squared is equal to capital R squared minus small x squared. I hope that makes sense. Just think about it for a second, and let's continue after that. Okay, so now that it's clear, let's rewrite this expression here again. So we're told now VC is 1/3 or pi by 3. R squared will be capital R squared minus x squared. And I'm going to have x plus r. Now the reason that I've done this is because I want to be able to maximize this with one variable. Here I have two variables. Okay, so I just removed one of the variables by keep using capital R because I know capital R is fixed. Okay, and with the help of that I got x inside here. Now how can I maximize the volume of a cone? Again, if you have studied calculus, you know that you can use derivatives, find the turning points, and then find out the maximum volume. Okay, if you haven't studied derivatives at this point, you can skip this question at this, but understand what I'm gonna do. If you want to understand, you can continue playing the video. Okay, so let me go to the new page. Let me write this new expression that I have as volume of cone is pi by 3 r squared minus x squared into x plus r. Okay, now I'm going to find the derivative with respect to x. So I can say dvc by dx, and using the product rule here, so I'll first find the derivative of this expression, which is going to be minus 2x times, that's all it's going to be, times x plus r. Okay, then I'm going to have r squared minus x squared, and then I'm going to have 1. Okay, just the 1, like this. And I can factor out something actually in this situation. I can actually just do this and then minus 2x like this, x plus r, and I can write this as r plus x times r minus x. I can factor out this x plus r outside, and I'm gonna have pi by 3 times x plus r, and then minus 2x plus r minus x, like this. Okay, and then I'm gonna have x plus r, and I can have r minus 3x like this. And I have to equate this to 0 to find the turning points. Well, x can't equal negative r, but x can equal r by 3. So this is my only valid solution, because I have to neglect the solution because x can't be a negative value. If I was just blindly solving this question as, calculus question, I would take this solution into consideration. But I know that lengths can't be negative, so I know this is my real answer. Okay, so I know my cone's volume will be maximized when the radius of the cone, or you can see the x, right? This part is 1/3 of the radius of the entire sphere. Okay, so now I can maximize it. Okay, so what I'll do is I'll take this expression and I'll plug it in, and I'll plug in r by 3 wherever x is there. So I'm gonna have, let me go to the next slide. I'm gonna have VC max. Okay, VC max is gonna be pi by 3 r squared minus r by 3 whole squared times x, well, that's just r by 3 plus r. Okay, so VC max will be pi by 3, okay, r squared minus r squared by 9 times 4r by 3. Okay, like this. All right, so VC max will be, this is going to be pi by 3. This is going to be 8r squared by 9. Okay, and this is going to be 4r by 3. Okay, so can I simplify this in any sort of way at this time? I'm just trying to think. I mean, I can, multiply it all, but if you go back to the first point, we're supposed to do this relation here. So I'm supposed to divide this by 4 by 3 pi r cubed. So let's just do that, okay? Let's just do that. So I'm going to divide this by 4 pi by 3 r cubed, okay? So that's going to cancel out, hopefully, the pi, the 1 by 3, the 1 by 3, the 4 and the 4, and the r's, okay? So what I'm left with now is 8 on the numerator and 9 times 3. Well, that's just 8 by 27. That's the probability. That's the final answer. Okay? Answer. Okay, so yes, this was a little hairy, but only because of this calculus part, right? If this calculus part wasn't there, if there's something more simpler, then we could have solved it within like 2 minutes. And yeah, this sums up geometrical probability. I don't think questions should be getting anything harder than this, because I've integrated calculus now as well. So it possibly can't get any harder than this. The IB shouldn't make it any harder than this. And yeah, that's about it for geometrical probability, and I'll see you in the next video. Bye-bye.